Good morning everyone. This is class number 8 on solutions and colligative properties, and today we will be learning about the third colligative property, that is depression in freezing point. Now before I proceed on with the topic, let us first know what actually freezing point is in terms of colligative property and vapor pressure. Now till now we had known that freezing point is the temperature at which a liquid starts to solidify and the process goes on and the temperature remains constant all throughout the process. Now from the concept of vapor pressure, which we had learnt in lecture number 6, we can define freezing point as the temperature at which the vapor pressure of the liquid state becomes equal to the vapor pressure of solid state. Now vapor pressure of the liquid state is something which we had learned previously from the concept of vapor pressure. But vapor pressure of the solid state, this part is a bit unknown to you. Now to understand this, we are to consider one very simple aspect of solid, that is sublimation. All solids are capable of subliming, however small the extent may be. Now since sublimation is the process of transfer of or conversion of a solid to the vapor phase, therefore sublimation also results in increase of vapor pressure, and that vapor pressure results from the solid state. Therefore, when the liquid state vapor pressure and the solid state vapor pressure, because of sublimation from the solid, becomes equal, that results in freezing point. Now here the question that you may ask is, why is there a depression? Because in boiling point we saw an elevation. So why not an elevation in case of a freezing point? To understand why there is depression, if we consider, say, a solidified solvent. Now anything which is in a solid state has got a definite geometry, a definite crystalline or a lattice structure. That means it has got some fixed geometrical orientation of the atoms. The moment you are adding a solute which is non-volatile in nature, where will the solute go? The solute will try to accommodate itself in between the solvent molecules. And as a result, the order that was there among the solvent molecules will now be broken. That is, the solvent molecules will now become disordered. And in order to get back the order in the solvent molecules, the kinetic energy of the solvent molecule must be lowered. How to lower the solvent molecule's kinetic energy? By decreasing the temperature, right? Or by abstraction of heat. Abstraction of heat, where will it result in? It will result in freezing point lowering, or what we call the depression in freezing point, right? Now this concept is almost similar to your elevation in boiling point. If I explain the graph of vapor pressure versus temperature, we will see that the solid solvent curve is always much more steeper because of the crystalline structure or the fixed lattice structure of the solid. Whereas the liquid solvent and the solution both are much less steeper than the solid solvent. The point at which the solvent in the liquid state and the solid solvent meets, that is the point of equilibrium, this is the freezing point of the pure solvent. From at this point, the pure solvent will start freezing and the process will continue throughout. Similarly, the point at which the solution will meet the solid solvent, that will become the freezing point of the solution. Now graphically or experimentally, when we draw this curve, we always see that the freezing point of the pure solvent is much higher than that of the solution, which is just the reverse of the boiling point elevation. Over there, TB naught was much less than TB, but here TF naught is greater than TF. Therefore, delta TF, or the change in temperature or the extent of depression in freezing point, is equal to TF naught minus TF, which is the first formula from the chapter. Next is the similar derivation as we have done for elevation, that is experimentally it is shown that delta TF is directly proportional to molality, which is number of moles of the non-volatile solute upon mass of the solvent in kg. Since TF is proportional to the number of moles of the non-volatile solute, therefore TF is a colligative property. So if I want to remove this proportionality sign, I introduce a constant called Kf, which is called the molar depression constant or the cryoscopic constant. Right? Cryoscope meaning freezing. The cryoscopic constant. Again, Kf is only dependent on the nature of the solvent and on nothing else. Unit exactly same as Kb, that is Kelvin kg per mole. Next is the definition of Kf. It has got the same definition as Kb, only in case of elevation you have to substitute it with depression. The depression and freezing point of a 1 molar solution. Right? It's the depression and freezing point of a solvent in a 1 molar solution. So Kf is equal to Tf when m is equal to 1. That's how the definition comes. Right? Now before we go into the numerical, we just go to the Kf determination formula. Similarly to Kb, Kf is equal to R Tf naught square into capital M upon 1000 into delta H fusion. R becoming the universal gas constant, Tf naught is the freezing point of the pure solvent in Kelvin, M being the molar mass of the solvent, and delta H fusion is enthalpy of fusion, which is further equal to the latent heat of fusion into the molar mass of the solvent. Clear? Exactly same as your elevation in boiling point constant, only all the B's will be represented by F in case of the depression constant. Now we move to the numerical part. The first numerical based on depression and freezing point: what amount of ethanol assumed to be non-volatile must be added to 1 kg water so that it freezes at -2 degrees Celsius. Kf for H2O is given 1.86 Kelvin kg per mole. So the solution is, just write down the formula, delta Tf is equal to Kf into M. Delta Tf, it's telling -2 degrees Celsius. Now over here delta Tf we have taken as 2 degree. Why? Because delta TF is equal to TF naught minus TF, which is, this is for how much? 273 Kelvin minus of 273, right? Over here we have taken it as minus 2, so that becomes a plus 2. This, if I take it as Kelvin, then this is Kelvin. If you take it as Celsius, then in case of a Celsius, you just, instead of making it 273, if degree Celsius, then you just write delta TF becomes equal to 0 minus 0 minus 2, that is plus 2, because freezing point of water is 0 degree in the Celsius scale. Now we just substitute the value. 2 is equal to 1.86 into W, that is what amount of ethanol, that is W by ethanol molecular mass is 46. Mass of the solvent water is given 1 kg, so write 1, and then W is equal to 49.46 gram. So this much amount of ethanol must be added to 1 kg of water in order to lower the freezing point by minus 2 degrees Celsius. Next sum. 50 centimeter cube of ethylene glycol is dissolved in 50 gram of water. The freezing point of mixture is minus 34 degrees Celsius. If freezing point of pure water is 0 degree and Kf of water is 1.86 Kelvin kg per mole, find the density of ethylene glycol. Here what we have to calculate is the density of ethylene glycol. Now before we have to calculate the density of ethylene glycol, what we need to know is the mass of ethylene glycol, right? Now in order to know the mass, ethylene glycol, with the formula is CH2OH CH2OH. So the molar mass of ethylene glycol comes to 62. So delta TF, which is 34, again similarly if you see, this minus sign goes away and you are left with only 34, is equal to 1.86 into W divided by 62 upon, it's given 50 gram, this 50 centimeter cube of ethylene glycol is dissolved in 50 gram of water. So this 50 gram of water, if I want to convert it to kg, I just divide with 1000, and then after calculation I get the value of W as 56.67. Now see over here, volume is given, mass you have got. So density is mass by volume. So what we do is mass by volume we divide, and the density of ethylene glycol is 1.13 gram per centimeter cube. Next, question number 3. 5% cane sugar by mass has a freezing point of 271 Kelvin. Find the freezing point of 5% glucose by mass if freezing point of pure water is 273.15 Kelvin. Kf of water given 1.86 Kelvin kg per mole. Understand the problem first. Cane sugar by mass is given and glucose by mass is given, both having same concentration. What you are to calculate is the freezing point of 5% glucose. Given to you is Kf of water and the freezing point of pure water, right? When you are given sum of this type, do not from the very first step start the cancellation and calculation, because ultimately in the last step all the factors get cancelled off and the calculation reduces. So it's kind of stupidity to do the calculation from the very first step in order to make things more complex. So now, cane sugar, the formula of which is C12H22O11, molar mass is 342 gram per mole. So delta TF is Kf into m. Pure water freezes at 273.15, but cane sugar freezing point is 271. So whatever we are doing right now till this much is for cane sugar. So that is equal to Kf into 5 by 342 upon 95. Why 5 by 342? 5% cane sugar mean 5% gram cane sugar in 95 gram water. So 5 by molar mass gives you the number of moles of cane sugar, and 95 gram by 1000 gives you the mass of the solvent in kg. Don't put the value of Kf over here because ultimately Kf gets cancelled off. So this part you are left with 2.15 is equal to Kf into, after calculation, 5 into 1000 by 95 into 342. Similarly for glucose, formula of which is C6H12O6, molar mass 180. You take delta TF is equal to Kf into m. Delta TF is equal to Kf into 5% glucose, again same thing, 5 gram glucose plus 95 gram water. So 5 by 180 divided by 95 by 1000. This is equation 2. Now what we do is we divide 2 by equation 1. When you are dividing equation 2 by equation 1, Kf gets cancelled off, 5 gets cancelled off, 95 by 1000 gets cancelled off. So you are left with basically 342 upon 180 in the right hand side. And in the left hand side you are left with delta TF upon 2.15. See now why I said not to cancel from the very first step. All the factors gets cancelled off. And then on calculation we get that delta TF is equal to 4.085 Kelvin. Delta TF is equal to the freezing point of pure water, that is 273.15. I just missed out on the 15. So if I write it here 0.15, so I just need to add further a 0.15 over here, and thus whatever the answer is, you get it, and that's it. Right? When you are going through the video, make it a point to solve the numericals that are already solved in the lectures, in this one as well as in the previous ones, by yourself. Don't take the online lectures too lightly, children. Thank you. Have a nice day and keep studying.